last session of the day. Before I introduce Miguel, I want to mention that Mark Olivia, the previous speaker, is available for hire. If anyone's looking to give him a job, he's on the market for next year. Miguel is a group leader in ICOGI, and he's going to tell us about a way to calculate things which involve an arrow of time.
Thanks, Ali. I'm going to speak about something that, to tell you the truth, I didn't really have anything on this topic, right? I may contributed a few years back, but lately I'm working on other things. And this is the closest we had, and it's still a work in progress. But we already got results. I think it's exciting enough to share them. And I also would like to get some feedback if possible, because I think that I cannot believe that I'm the first one to come up with these ideas. So we'll start. At some point in my life, I was working in 3 problems that I thought that they were completely disconnected. And recently, we discovered actually that they form part, or they're variants of a sort of super problem or meta problem. And then we found the solution of the problem. But I'm going to speak about only one of them, which was this one. It's a really weird problem. Well, actually, it's very natural, but what is weird is that nobody has considered it before. So you start with a finite-state automaton. This is simply some system that has some internal state that can take finally many values, as the name indicates. And then it has an external input, also that belongs to some finite alphabet. Now, when you input something to this automaton, 2 things will happen. Well, first of all, the internal state will change, and also it will produce some output. And how these 2 elements will change will be given by this probability distribution. There will be a conditional probability distribution on the initial value of the state and the input, and it will determine. Well, not determine. It will give you some distribution on the final state and also the outcome. In terms of a Bayes network, is actually kind of ugly to draw. So these are the 2 observed variables, and these are just latent variables, right? I mean, one of them is the internal state, and now these 2 form a sort of transient thing that generates both the new internal state and the output. If it were just this, it would be really boring, right? I mean, something that you input something and you get some result. It could be a calculator. But the cool thing about the automata is that you can iterate the process, right? I mean, suppose that you start with an automaton in some state sigma 1. We put some symbol y1 and we get some output, and also there's a transition. But now we could do the same, right? I mean, we input a second symbol and then we get a second output, and so on. And when we get tired, then what we have is a collection, it's a list of outputs and also a list of inputs. Now, if you consider what is the correlations. The correlations, the probability distribution of these outcomes conditional on the inputs, then you have what people at least in my field, that we call temporal correlations. And of course, if I gave you the transition matrix of the automaton and I give you the distribution of the states, the initial state, you could calculate this obviously, right? I mean, very, very simple. And again, as a Bayes network, yes, for this conference, right? I mean, well, it's kind of similar, right? I mean, you see there's a clear arrow of time, right? And meanwhile, you get some statistics. And of course, I'm making the assumption that whatever functional relation is generating these 2 variables based on these 2 is going to be the same one over and over. Okay, in this paper, how weird, it says the color. It should be blue. Where is it? Well, okay, so according to these papers, we pose the problem of characterizing the set of correlations that you can get using a d-dimensional automaton. And well, it's kind of easy to see that if the dimension of the automaton is big enough, then essentially you can codify whatever you like. And whatever you like means you can generate any correlation, any temporal correlation that satisfies a condition called set of, well, no signaling to the past. Signaling input to the past means that the input that I put in the future cannot affect the statistics of the outcomes in the past, which makes a lot of sense, right? I mean, and you cannot expect to go beyond this. But the interesting thing is when this number, this d, is actually below this value, then it's a really complicated problem to characterize what kind of correlations you can get with one of these automata. But there you have an idea what kind of things these people are interested in. In this paper, these 2 papers, the authors consider a scenario in which the automaton has actually no inputs. It's actually a hidden Markov model. You could think of it, but more or less, it's not exactly the same. And the idea of this automaton is that it's going to be transition between the states and outputting some bits. And we wish the automaton to output n-1 consecutive zeros, and then finally a 1. I want this because this is a model, a good model of what an alarm clock is. Something that waits for n-1 seconds and then emits a signal. Of course, if the dimension of this automaton is smaller than n, you won't be able to do this with certainty. So this automaton may produce the sequence, but only with some probability. The question is, what is the maximum probability? A limit on the amount of the number of states of the automaton. What is the maximum probability that we have of producing this sequence? It's not a complicated problem, but nobody had considered these problems in the past. It's very weird. We really want to read old books of computer science, right? I mean, there are lots of material about finite-state automaton, but these kind of problems like optimizations over the automata, well, I couldn't find them before. Okay, so let's think about what this problem entails. So, well, sorry, I have to give also for the motivation. Actually, if you go to the paper, you will realize that more than finding the actual value of this quantity, you want to know what is a good upper bound, sufficiently good upper bound for this. Because now, I'm not going to get into the physics, okay? But the thing is that the same way that I define a classical automaton, you can define a quantum automaton, where, and this is only for the physicist, the internal state of the system is codified or represented by a D-level quantum system. And the thing is that if you go to the lab and you build this automaton, and then you observe that the probability of getting the one-tick sequence is greater than any upper bound that you could find on the classical value, then you can claim that you got a quantum advantage, which is essentially what my field is about. My field is about proving quantum advantages. And for that, of course, you need an upper bound. Okay, now the problem. So if you expand it the way the people in optimization theory like, it will be exactly this. These are the variables of the problem, these probabilities, and also these probabilities here. You want to maximize this expression. It's a polynomial. So it looks good. It's a polynomial. Polynomials are nice. They're our friends. And you can realize that actually you can get rid of these variables because you can always assume that the automaton starts in a given configuration. And by symmetry, you can take it to be number one. It doesn't really matter. So in the end, it's only these variables. Well, it turns out that's really complicated already because these conditions here define some convex set of possible values for the variables. But the problem is that this objective function is non-concave. So if you try to apply standard methods like gradient descent, you will probably get stuck in some local maximum. And of course, if you go to the lab and you get this value, and of course you don't know that it's a local maximum. You just know that it's the value that I got in my computer. But now I go to the lab, I generate the one-tick sequence, I calculate the probability, and I find that it's greater than this. It doesn't mean that we have certified a quantum advantage. It is something that is probably an upper bound of this value here. Okay. So now, of course, there are methods. People have come up with methods in optimization theory to get upper bounds for this kind of optimization problems. And the problem is that all of these methods scale really badly with the degree of the polynomial. In this case, the degree of the polynomial is the same as the number of time steps. So it's really bad, right? I mean, if you try to use standard methods, then you're stuck to predicting what happens when you have two ticks, which is not that interesting. Okay, there's an extension of this problem because if you think about how you count, how do you verify that you have the sequence 00001, you could imagine that another automaton is verifying that the first automaton where you're optimizing is actually producing this sequence. So you could consider some optimization where you have you want to optimize for a D-state automata, an objective function that is determined by interactions of this automaton with some non-automaton. Let's put it it's a bit difficult to, but it's not difficult. Look, we just take the automaton that we control, then we input some symbol, then we get an output, and then we feed the output to the input of the automaton where we want to optimize. Now it produces an output. The output we feed it into the input of the automaton we control. We get another output, and so on and so forth. And at each point, because this part we can control, this automaton we can control, we can in principle open it and check the state. So we can associate like some sort of score for its possible value of the state. And the goal will be to maximize this score on average, right? I mean, over all possible automata that you can have here. Of course, this part, this other automaton is fixed, right? This is actually the definition of the problem. If you want some example, then the simplest I could think of is suppose that for some reason you're interested in finding what is the maximum average score that you can get in Street Fighter using a D-state automaton. So this could be controlling Ken, and then you could use the Capcom Fire Engine to control Ryu. And then you want to see what is the maximum you can do with, I don't know, a 3-bit automaton. Probably it's terrible, but I don't know. I don't know the answer, and I bet that you don't know either, right? I mean, why? Because we don't know how to solve these problems. So to solve this kind of problems, we invented some sort of formalism. Okay, but I'm going to tell this a sort of meta problem that that allows you to formalize the problem that I just solved. Okay, so a sequential model is some system that has some internal state. This internal state is going to transition, and well, I will speak about this later. It also has associated some sort of penalty, and the penalty depends on the state but also depend on some unknown evolution parameters. You will understand why I call them evolution parameters, and some uncontrolled variables. These are variables that do not really have a distribution. It's related to, okay, it doesn't really matter. It's related to actually to free will in a sense, right? I mean, these uncontrolled variables are going to conspire adversarially against you, and you'll understand in which sense. Okay, now there's a transition, and this transition is mediated by some known equation of motion. That so the new state will depend deterministically on the previous state, on these unknown variables, uncontrolled variables, and also on these unknown evolution parameters. And we assume that this equation of motion actually could be time dependent. So it depends on which time state you are. I mean, it will have this transition, and even the very definition of a state could depend on which time step you are in. Now, like with an automata, you can also iterate operations on one of these sequential models. You will get some sequence of penalties. And the goal is to maximize what is the sum of all these penalties over all possible values of this variable here, and the unknown evolution parameters, and also over all possible values of these uncontrolled variables that you have at each time step. Now, if I removed this variable here, then what you would have is a Markov decision process. It's something known already in mathematics, and yeah, then but I want to speak more about this. Okay, so how does it fit the problem that I gave you before, right? I mean, we're thinking of optimizations over finite-state automata, this one here, over some function that depends on this interaction with this other automaton. What does it have to do with sequential models? So you have to find some sequential model that is kind of associated to this kind of scenario. Yes.
The non-type is random, it's local random.
No, it's not. No,
It's not.
No. It could be. For example, I don't want to put this example, but if you're dealing with disease transmission models, models for disease spread, one of the models would be the reproduction number of the virus. You don't know what it is. So it's an unknown evolution parameter, and it is the same at each time.
So it's the same for each box.
It's the same for each time. Yeah, it's the same at each time. It's always the same. Okay, so we're going to formulate this thing as a sequential program, right? And what we have to do first is to find some sequential model that describes this interaction between these two things. And the easy thing to do, there are other things actually more efficient, but the easy thing to do is to take as a state of the system the probability distribution over these three variables: the input of the first, the automaton which you want to optimize, the state of the automaton, and the state of the automaton that you control. This is going to be our state, the state of the sequential model. And if you take this as a definition for a state, you see that indeed you can develop an equation of motion. Given the state that at a given time, you can use some parameters that are always the same. So these are the unknown evolution parameters, and some of the parameters that you already know because they're defined by the problem in order to find the next one, the next state. And in this case, we don't have really these uncontrolled variables. In this case, this is just a particular variant of the meta problem that I showed you before. Now, there are other sequential problems. I don't have time to speak about any of this stuff, but I was trying to solve them. And when I started investigating this thing, one of them is the problem of detecting entanglement in a spin chain. Now, this is only for the physicists, but it will be very, very short. You have a lot of spins, you have a lot of quantum systems, and then you want to do one velocity measurement. We want to measure each of these systems one by one. And at the end, you want to make a guess on whether the whole state is separable or not. Okay, this is one problem that you can also formulate as a sequential problem. And another one, it's a sequential problem actually where you don't have these unknown evolution parameters. So in principle, you can think of it as a Markov decision process. But the problem is that the standard methods for Markov decision process are not suitable for this kind of for the kind of problems that I have here. So you have to use the techniques that I will tell you now. And the other one, and actually this one in which you have really all the non-evolution parameters, the nasty variables, etc., is the problem of bounding the cost of a government policy for disease control. I could formulate this mathematically, but we don't really have time. And if you're curious, I can tell you later. But well, it's actually the most important thing. Okay, so how do you solve these problems? So I'm going to give one method. Okay, this is the original problem we want to solve. We want to maximize the total reward over all the values of these variables here. And we're going to introduce a function. This is going to be we call it a value function. It will represent the maximum penalty that you incur into from time k onwards. So all the cumulative things, cumulative penalty that you will get from time k onwards, condition on the current state being sk and on the value lambda of the non-evolution parameters. It's a definition. With the definition, then you can make an observation. So the maximum penalty that you will have at this moment in the future is equal to the penalty that you will have now, plus the penalty that you will have in k plus 1 times, which by definition is given by vk plus 1. Vk plus 1 acting on the next state. And the next state is a function of the current state, these uncontrolled variables, and also these lambda variables here. So all you have to do is to maximize over the unknown uncontrolled parameters, and then you get the new function. You can define all these functions iteratively, in principle. Again, if you drop these uncontrolled, these non-evolution parameters, then you end up with what is called the Bellman equation. Okay, so one method to solve this kind of problem is precisely to take advantage of this observation. Suppose that we want to minimize the minimum of some real number, nu, under the condition that nu is greater than the value function for the first time step. And then with these constraints, right? I mean, namely that whatever function we have in the kth step is going to be greater than the penalty plus the function on the next time step evaluated on the next state. And this has to be true for all possible values of these variables of the uncontrolled variable, and also for all possible values of the non-evolution parameter. So if you follow the chain of inequalities, you will convince yourself that actually any value of nu that is feasible, that satisfies these constraints, so for which there exists functions like this, right? I mean, that satisfy these constraints, will give you an upper bound of the solution of the problem, of the sequential problem. And if you choose these things, this v1 to vn to be the value functions of the problem, then actually you will get exactly the v will be equal to the solution of the problem. So this is actually another reformulation of the original problem. And what is the complexity of this reformulation? Well, it will depend on how difficult it is to optimize our functions, which is in principle something difficult, right? And how difficult it is to enforce these constraints. But whatever the complexity is of these two things, as long as you can bound it, then the total complexity of the algorithm will be n, the number of time steps, times this complexity. It's of linear in n. And you're not going to get better than this. This is really the best scaling you can hope to get. Now, I mentioned that, well, this method based on value function, there's another method that is another reformulation of the original problem that is based on the optimizations over marginal probability distributions. I'm not going to speak about it. It's very interesting to derive it or to show where it comes from, right? I mean, but I won't speak about it because actually these two things are the dual of each other. So you regard this as an optimization problem. It is a convex optimization problem, in fact. Then you find that the dual, you build the Lagrangian, then you find that the dual of this problem is actually this one, and vice versa. But sometimes it's good to bear in mind this other formulation because it gives you some intuition about how to tackle the problem where you don't have enough computational resources. Okay, now there's a problem with this formulation because, well, there are two problems. The first problem is that you're optimizing over functions, and this is very difficult. I wouldn't even know how to do it actually, unless these states can only take finally many values or something. But we're speaking about states that can take a continuum of values, so it's really complicated to optimize our arbitrary functions. And the other problem is that, well, I will speak about the other problem later. But the first problem you get rid of very easily. All you have to do is to optimize over some subset of functions that you know how to parameterize. And the simplest set I can think of is the set of polynomials of degree 2n, because in this case you only have to take care of the coefficients. So it's a finite dimensional optimization. It could be very difficult, but it's finite dimensional. Still, it's a big problem, even if these things are polynomials, to certify that one of them dominates the other. This is really complicated in general, but in any case, even if you could solve this problem, then because you're optimizing over a smaller class of functions, then you will get you wouldn't be able to reach the minimum in general, so you will get an upper bound of the solution of the problem. But the good thing is that polynomials can approximate whatever. So this the sequence of upper bounds as n goes to infinity should converge to the solution of the problem. Okay, so it's a sequence of upper bound that is converging. Again, it's difficult to certify this part, right? I mean, so that's why you wouldn't try to solve this either. But now what you do is, in order to certify these inequalities, you use a positive Stellensatz. Now, positive Stellensatz is some really nasty German word that means that we have some criterion that is tractable that allows you to certify that this holds. It is a sufficient criterion, but it's not necessary. So it means that sometimes it doesn't. It may be that this satisfies the criterion. That this actually holds, but you're not able to prove it. Okay, but well, because now we're optimizing over the set of functions such that this thing is not only true, but you can also detect it with a positive Stellensatz. then you're getting even another upper bound on the solution of the problem. But if you choose your positive Steller sets in a clever way, then nonetheless, in the limit, the sequence of upper bounds will converge to the solution of the problem. Now, about this positive Steller set, there are many in the literature. Some of them, depending on which one you take, this problem will turn it into a different problem in complex optimization. For these two, for example, this problem will turn into a semi-definite program, some sort of optimization over positive semi-definite matrices that we know how to solve efficiently. There's another more exotic positive Steller sets that if you try to apply to this problem would transform the problem into a problem of geometric optimization, which is a bit more complicated, and also there are others applications. So let's go back to the original problem that I posed you before. We want to maximize the probability that this state automata outputs the one-tick sequence. In this paper, the authors, what they did was to consider epsilon nets of the set of possible automatas, right? I mean, you can parameterize its probability, and right, and then well, they had to do really lots of crazy things in order to get these numbers, right? I mean, but they managed to get the optimal values of this probability for dimension 2. They had to use really complicated computers, a cluster, and parallelize everything, but they managed to get it. Okay. Using the method of value functions together with Schmutgen's positive Steller sets, then we managed to reproduce all the numbers in maybe 1 hour with a laptop. Actually, with this laptop. Now, in the paper, they do something else. They managed to get some guesses on what are the maximum values for other automata with higher dimension. In this case, they couldn't make epsilon nets because as the dimension increases, well, the complexity becomes exponential in the dimension. It's really terrible. It's a drama. So what they did was to use gradient descent in order to get these numbers. But of course, they're not sure whether these numbers are actually the optimal, right? I mean, it's a conjecture that these things are actually the maximum value that you can achieve with this state automata. Well, using the same method, but this time with a big computer, this thing died at some point. Then we managed to reproduce this value, and we managed also to get numbers for the other ones, but they were a bit higher than the numbers that these people reported. And it is not clear who is right or who is righter, right? I mean, it's not very clear. It isn't very clear whether our bounds are strict upper bounds or on the other hand, they're actually the real bounds, and these people just couldn't find it because they were using some variational method. But in any case, the fact that you can recover everything in dimension 2 shows that if you start studying the value function that are output by the computer, probably you will be able to derive a general formula and then solve the problem analytically. And I count on you. Okay. Okay, entanglement detection and spin chain. I will go fast because I know that some of you don't know physics and maybe you don't care, right? I mean, so this is only for physicists. It will be fast, okay? So we want to detect entanglement in a spin chain. And one way to do it is to take a finite state automaton, and then this finite state automaton will tell us at each time how to measure its particle, and depending on the outcome, it will tell us how to measure the next particle and so on. Okay, and at the end of the day, you follow this progression, and at the end of the day, based on the final state of the automaton and the last measurement outcome, you make a guess whether the particle was, or the whole system was entangled or separable. Okay, so we came up with some entanglement detection protocol for jet sets. For different numbers of well, it's kind of trivial to see that jet set we will get the entangled tag with probability 1, and the problem was to compute what is the maximum probability of declaring entangled something that is actually not entangled, and this requires an optimization over separable states, which is really nasty. It is obvious to get a lower bound of this maximum, which is 1/2, but apart from that, we didn't know anything else. Well, this is what I got with actually with this laptop again. This is an upper bound that I got using this other formulation that is based on probability distributions that I didn't want to talk about. And you can see that, well, it very quickly goes for high end to something that must be really close to, well, it is really close to the optimal value because we have a lower bound which is equal to 0.5. The interesting thing about this graph is that I managed to go to n equals 40 with the laptop. Yeah. N is the number of particles in the spin chain. No, this is one copy. No, this is one copy, and you get a probability. You have to repeat it several times in order to decide, right? I mean, if in practice, right? I mean, you have to have several preparations. Yeah, because yeah, the probability still is 0.5, right? I mean, but you don't have to take that many, right? Because it's still low enough. Okay, the interesting thing about this graph, as I said, is this number, and because just so you have an idea, about here it would be what I would get with a normal computer. or maybe with an extended computer. Well, maybe with a computer the size of the size of Spain, right? I mean, here I will be able to get something with 15 systems, right? I mean, the complexity increases exponentially. So if I now went to here with using brute force, then I would need 10 to the 20 computer the size of Spain, right? I mean, so it wouldn't work. But and again, I got this with this laptop, right? I mean, it's not special, it's not magical or anything like that, right? I mean, I didn't get it from a strange toy shop where there was the devil or something. No, it was something that you can get. Now, the next step is to complicate the problem. So suppose that we take the sequential model and then we add a policy. A policy essentially is something that you can control, okay? That is going to affect both the penalty and also the equation of motion. And remember, the goal of the sequential problem is to maximize the total penalty to get to the worst case scenario, which is the worst penalty that you can get. The sequential problem with varying policies, the goal is to minimize over the set of policies what is the maximum penalty that you're going to get. Now, this is, of course, unrealistic because just computing this for a given policy is really very complicated. But a more realistic goal is to try to minimize some upper bound on the solution of the sequential problem. Because in this case, if you have solve this problem, then you will have a policy that you can go and implement. And also you will have an upper bound on the maximum penalty for following the policy, which is good, right? I mean, you can say, look, Eli, if you go to a shop and then you steal a sandwich, then you will get incarcerated for 2 years, right? I mean, and you know what is the maximum penalty, right? I mean, and you know the policy. You go to the shop and then you steal the sandwich, right? I mean, it's something that you can apply in your everyday life. Don't do it. Don't do it. Okay, so we're thinking actually about the disease control problem. Yeah, the idea would be to go to a government with a control policy. So some policy that tells you, you have to declare confinement these days and under these conditions, and then you have to vaccinate the people. It's like if you follow this policy strictly, then at most the number of yearly deaths is going to be this amount. Okay, now the way to solve the problem, but this is a really complicated thing, so I'm going to be extremely unoriginal. The way to solve we propose to solve the problem is to use gradient methods. So if you have this function, all you have to do is starting from some guess on the optimal policy, then you update it sequentially using the gradient of this function. You can use this method, which is what people call vanilla in machine learning, and you could use Adam, which is something that wouldn't fit in this slide, or which is much more complicated. That uses momentum and things like this, right? Which is what we will propose. The problem of this thing is how to calculate this gradient, because it's not trivial. Because okay, this is the original problem, but we relax it. We relax it in a complicated way, right? And we relax it into an optimization problem. And then it's complicated to calculate the gradient of the solution of some optimization problem, right? Well, in the paper that is to appear, right? I mean, we consider a large class of relaxations of the original problem, and then we find that you can calculate the gradient, and there's some mild assumptions about what the properties of the 10 minutes. Okay. There's some mild assumptions of the properties of the optimal solution. You can calculate it. And the bottom line is that the complexity of computing the gradient is comparable to the problem of computing actually the bound. So if you have enough computational resources to put a bound on the maximum penalty, then you have enough computational resources to optimize over policies. Okay, so for the future, and this is the part that we haven't done yet, but we're on our way. We'd like to try to completely automatize the entanglement detection protocols. The idea is that you give me some reference state that you want to detect the entanglement. Then I conduct some optimization over protocols that have the property that they will declare it separable, the reference state with very low probability, and at the same time, they will, whenever they say that it's entangled and the state happens to be separable, this would happen with very, very low probability. So it's actually one of these problems that you can also formulate in the way that I saw you before. It's one of these optimizations over policies in sequential models. And we're thinking of replacing the finite-state automaton by a recurrent neural network, because I think it's easier, right? I mean, well, it looks more practical, right? And in a recurrent neural network, the state of the system, internal state, is given by a continuous vector instead of just simply some discrete value. And probably this gives you much more flexibility, and also it allows the machine also to output some input that is also continuous, which is good because the measurements that we do in the lab actually depend continuously on some parameters. And of course, we still have to do this part, but the problem is extremely complicated to try to make some sort of software or at least to try to see how the algorithms work for disease control. I don't have the slightest idea what kind of things we can get. I have a paper that I forgot to mention here, exactly about these kind of things, where we try to do everything done rigorously. So in the end, you got a sort of lower bound, you got a lower bound actually on the number of yearly deaths. But of course, you cannot go to a government with, if you follow this policy, it could happen that you kill 1 million people or something. But no, they want to know for sure, right? I mean, and they want to, because otherwise it's ridiculous. And I'm going to stop here. Thanks.
There you go. Questions? You mentioned the Bellman equation.
The Bellman equation, yeah.
Where, what, why? What is that?
This is an equation that appears in these Markov decision processes. Essentially, it's well, let me see. Yeah. So essentially, it's like this. You have a scenario like this, but you don't have this lambda here. And that's pretty much it. It's something that people have studied in mathematics, right? I mean, you also used to model things that change in time. And the problem with the automaton is that this didn't work because there's something that is always the same at every point, right? I mean, which is in this case the transition matrix of the automaton. So for the problem that inspired the whole thing, this formalism was not good enough. And I think is that normally, in order to solve the Bellman equation, let me see. Let's solve the Bellman equation. The good thing about the Bellman equation is that under some conditions, yeah, exactly. If the number of possible states and the number of possible controlled, they call actions, right? I mean, control values, the number of possible values of this variable are finite, you calculate this thing exactly because it's just a finite optimization, a finite optimization or finite possibility. So you can calculate things exactly, right? I mean, in our case, we're interested in continuous things. So most of the literature and the topic does not help us.
Yeah, at the end, you are considered continuous state automata, essentially.
Yes, that will be a recurrent linear network.
Can't that defeat anything? I mean, the whole point, it seemed to me in the beginning, was that if you have a finite state, then there are some tasks which it cannot possibly succeed at,
Yes.
other than with reasonably low probability. And now you have the possibility of finding a quantum advantage,
Yes.
because the classical system will do very poorly, whereas the quantum system will do maybe poorly, but much better at achieving the probability of
That
achieving.
is true.
But if you have a continuous internal state, how do you start having?
You can codify everything, I guess, right? I mean,
Yeah.
you could codify, yeah, it's true.
So why are you looking to generalize to that?
No, because the original thing was to show that if you go to the lab and construct a finite state automaton, a quantum one, right? I mean, you can do magic, right? You can do better than classical. So for that, we need to focus on this automata. The techniques that I showed also work for continuous automata, provided that you know what is the. I guess you need to make some assumptions, right? I mean, because if you allow whatever, then I don't think there's any limits, right? I mean, you could assume that the functions that determine the transition are kind of smooth or whatever, and probably then you will get some non-trivial restrictions, I guess.
And lastly, when you were doing optimization over functions, you chose to look at polynomials of degree 2n.
Yeah.
Was the 2 sort of arbitrary? Like it's just something that you can consider, take an asymptotic limit of, like why 2n?
Why 2n and not 10? You mean, or I don't understand?
Why not
Okay.
10?
I see. Well, it's because if I fix the degree, right? I mean, then the whole function can be defined with a finite number of coefficients, and if I don't, then so I wouldn't even know how to start the optimization if I didn't have this information. If I don't restrict the functions this way. But there are, okay, I have to say, I mentioned this word, horrible word, the positive Stellensätze. There are also positive Stellensätze, correct? Yeah, okay. Positive Stellensätze for functions that are not polynomials, actually. This is really curious. There are positive Stellensätze for functions that are linear combinations of exponentials, and then you can vary the coefficient multiplying the exponent and also the exponent itself. They may have some applications.
Other questions?
I think this is a bit connected to the discussion. In the case of general quantum supremacy, people, it depends a lot on what the task is, right? I mean, sure, hit on something that's really important because cryptography depends on not being able to factorize, right? But the fact that you can do so much better in a quantum context is very deeply embedded in the mathematics of what you're calculating. And so you started out with your alarm clock, right? I mean, that's a very simple problem, and it's kind of interesting to think about. from a quantum point of view, if you had stuff bouncing around and you could have different kinds of interference, and maybe, you know, the interference would clear after some time and you get a good probability for tunneling. But is there some, I mean, that was that problem chosen just because it's easy to state, or is there some idea that here are some problems where a quantum finite, I mean, if a quantum thing like this could do much better than a classical thing like this, or, you know, are there some class of problems that look like it might be?
I understand the original reason why they consider this kind of things was because it appeared naturally, this problem when you try to use quantum systems to measure time. Because at the end of the day, everything is quantum, and but they wanted to see how well you can do with a given dimension when you have only control of a given dimension, and this is a really complicated problem. And I don't know, actually, to come to think of it, maybe it was not that important to find the maximum probability for the one-click sequence on the classical version, but more on the quantum version. But with these techniques, you can also do it in principle. We haven't done it, but well, I'm not sure. Possibly you can do it. It depends on whether the computer is able to has enough memory to carry the first steps. If it does, probably it will go through, and if not, but.
Thank you so much.
Okay.